So far, we've been talking about inference in terms of the strength of evidence, and we sort of proposed some loose guidelines for describing how strong the evidence is based on the p-value. So if your p-value is larger than 0.1, I would probably say that that is weak evidence, right? Because if something happens more than 10% of the time just by random chance alone, that's not great evidence that there's something else beyond chance that's happening here. So that would be weak evidence. If it's between 0.05 and 0.1, I would call that moderately strong evidence. These events would occur occasionally by chance, but it's still on the somewhat unlikely side. If the p-value is between 0.01 and 0.05, I would probably call that strong evidence. And if it's less than 0.01, something that would happen less than 1% of the time by chance, I would call that very strong evidence. Clearly, this is just a continuum, right? The smaller the p-value, the stronger the evidence. And anytime we talk about the strength of evidence in this class, we always mean the strength of evidence against the null hypothesis and for the alternative. So since this is just a continuum, there's really nothing magic about any of these cutoffs. It can be sort of helpful to have guidelines just for describing how strong your evidence is, but it's important to think of this as a continuous thing. At the same time, sometimes we have to use a p-value to make clear-cut binary decisions. And so another approach uses a p-value to either reject or fail to reject the null hypothesis. So it turns it into a dichotomous decision. And to do that, we need some kind of a cutoff. So our significance level alpha is a value that's used as a criterion for deciding how small the p-value needs to be before we consider the evidence convincing enough to reject the null hypothesis. So there's lots of different cutoffs that you can see, but a common cutoff, by far the most common I would say, is alpha is 0.05. So basically you say if it would happen less than 5% of the time by random chance, that's strong enough evidence to reject the null. But whatever we set our alpha level to be, if the p-value is less than that alpha level, then we would reject the null hypothesis. And that means that we have sufficient evidence, sufficient meaning it's met our criterion, sufficient evidence to conclude whatever our alternative hypothesis is. And so in this case, where we have enough evidence to conclude the alternative, we call this statistically significant. So we would say that our results are statistically significant in this case. Whereas if the p-value is greater than alpha, in that case we're going to fail to reject the null. And in that case we don't really have sufficient evidence to conclude anything. So we have insufficient evidence to conclude what we're trying to conclude. Insufficient evidence to conclude HA. Note that when the p-value is large, we're not proving that the null hypothesis is true. All we're saying is that the null hypothesis is one plausible explanation for the sample results that we got. So it doesn't mean that it's the only explanation, just that the null is plausible. And when the null is plausible, we say that those results are not statistically significant, right? We didn't have enough evidence to completely reject the null. So what's the problem with this? What's the problem with classifying results as significant or not significant? Well, one is sort of inherent in the fact that we're taking a continuous p-value and turning it into a yes or no, reject or fail to reject decision, right? Because by setting that cutoff, let's say we set it at 0.05, we're sort of sending the message that a p-value of 0.051 and 0.049 are really different, right? That they're different in important ways, but that's not true. It's a continuous thing, and so the strength of evidence for those two p-values is virtually the same. But making a big deal out of one cutoff like 0.05 can give people incentives to try to get to that value, because if it's statistically significant, it's more likely to be published, it's more likely to get attention. So we're almost creating these goals for researchers to meet, and that's not a good way to get valid analyses. Another issue is more of a communication problem. So what do people hear when you say statistically significant? What comes to their mind? Specifically, are we thinking about strong evidence in that case, or a strong association? So I have an example here. This is from a study in Tennessee where they were trying to figure out the effects of class size. It was called the Tennessee Star Study. But as part of that study, they recorded how long different types of students were in the study, meaning they didn't move to a school that was outside the study. And if there were important differences between student groups, it would make us question how reliable the study's results were for those groups. So for example, here I've broken it down by student gender, male and female, was how it was recorded here. And we've got really big sample sizes, over 5,000 in each group. You can see that the means are different. The mean for females is 2.37 and the mean for males is 2.26. And then the standard deviations are also given there. So when you actually do a hypothesis test, the p-value is 0.000045. So it is an extremely small p-value. So is this difference between the groups statistically significant? Yes, it doesn't really matter what alpha level we're talking about here. That p-value is going to be smaller than any reasonable alpha level, right? We usually see like 0.1, 0.05, 0.01. This is way smaller than any of those alpha levels. So what does that actually mean? So if we think back to the interpretation of the p-value, that's telling us that these results would be extremely unlikely to occur by chance alone, right? It doesn't seem like this is a fluke. It's weird. I actually don't have a good explanation for why this relationship would exist, why female students would be more likely to stay in their schools, whereas male students would be slightly more likely to move, that they would stay in their schools for less time. But it doesn't seem like it's just a fluke, because these results would be very unlikely to occur by chance if the null were true, meaning if there were really no difference between these groups. So then this gives us very strong evidence that the means are different, right? That the means are different for males and females. So we've got, it would be very unlikely to occur by chance. We have very strong evidence then that there is a real difference between these groups. But would we say that the difference is practically important? So if we look at how large the difference is only, let's go ahead and subtract it, 2.37 minus 2.26, so 0.11 years. So practical importance is going to depend on knowledge of the context, and I don't really want to go into details about the context of this study here, but just at a glance, I mean, 0.11 years doesn't seem like a very big difference. So I would probably say here that there's not a strong association between these two variables, not a strong association between gender and time in the study. Right? We said that a strong association in data like this means that you have a big difference in the centers, right? That which group you're in makes a big difference in terms of the response variable. I wouldn't say we have that here. It seems like gender makes only a small difference in the average time spent in the study. So how does this happen? How do we have strong evidence but a weak association? So this tends to happen in this specific circumstance where you have a really large sample. So remember, when you have larger sample sizes lead to stronger evidence. So our evidence can get stronger even if the difference between the groups, even if the size of the effect is pretty small. So when you have really large samples like this, it's sometimes possible to have strong evidence and not a strong association. Unfortunately, when people hear this term statistically significant, they think that means, oh, it's significant, it's an important difference. But that's not actually what the term means. And it can be so confusing to people that actually some statistics organizations have recommended that we just stop using this term altogether because it's causing so much confusion. So that's another issue with the term statistically significant.